So, welcome to lecture number 3 of module 10, in which case we are discussing about scan chain based sequential circuit testing. So, in the last lecture and one lecture before that, we found out that for testing sequential circuits, as there is a flip flop, so which actually make it difficult to control the secondary primary inputs and the secondary primary output difficulty to observe. So, because of this reason we have found out that sequential circuit testing or ATPG is more difficult than combinational circuits. For combinational circuit, a single test pattern can be easily determined which can detect your fault. So, that is why sensitize, propagate and justify approach. Now, if you look at the sequential circuits which you have already seen in the last two lectures, we saw that if you want to test a sequential circuit, then what you have to do? You have to first go for time frame expansion method, that is you have to slowly control the virtual primary inputs, or that is the secondary inputs which are the output of the flip flops. So, they cannot be directly controlled. So, what you have to do? So, you have to use a time frame expansion, or you have, that is by a series of sequences, you have to control these inputs, virtual inputs, and then you can apply the test pattern of the primary inputs, and then you can test the circuit. And we found out that this process is a complex process, because at you have to control the flip flop outputs which are the secondary inputs. There is a series of patterns may be required to do, and you can find out that in the last stage there can be a conflict which can lead to the restart of the whole procedure. So, leading in a lot of wastage of the computation time. So, then we have found out that, then we discussed in the last lecture that to avoid all this complex business, we said that can we directly control the flip flops by using the set and reset line. So, this was a very good feasible approach, and we saw that it can be easily done in two patterns. We can easily test that circuit, in which case in the first pattern you set and reset the flip flops as required, and then you apply the primary inputs in the second pattern and do the testing. But then we found out that if there are n flip flops, then you require 2n number of pins in the circuit to do that, which is an extremely complex procedure, because I mean if the circuit has around 10 to 20,000 of flip flops, then having 20 to 40,000 extra pins is not a very feasible approach. This is because the packages with more than 1000 pins, even we have the limitation of about 1024 packages, I mean that we generally have in the market. So, going beyond that is very expensive, and having about 10,000 pin outs is an infeasible situation. So, while the idea was good, which converted a sequential circuit to a virtual primary circuit, combinational circuit, and did the testing, but the huge number of pin outs actually created a massacre. Then what we have done? Then we have said that now let us not control the set and reset line of the flip flops by primary inputs, making them as primary inputs. Rather than let us using a shift register, and we load the shift register in a sequential fashion, and the output of the shift registers will be connected to the set and reset lines. So, that whatever set and reset lines have to be controlled, what you can do, you can as required you can scan in the values, or you can shift in the values in the shift register and do that. But then we found out this is a good approach, because the two things are there, the pin outs are not increased much, because you require another pin out for the putting the values in the shift register, you need a different clock for the shift register, and there is an extra output for the shift register. So, with 3 more pins you can do the testing, that is you can control the set and the reset lines individually using this shift register. But now here the problem is, if you have n flip flops, then you require 2n number of extra flip flops in the shift register, making its area overhead very high. Also, secondly, I mean to control the flip flops, now you require 2n number of clock pulses, because you have to shift in the values of zeros and ones for the set and the reset lines. If there are n flip flops, we saw that there are 2n lines considering the set line and reset lines, and then you have to shift in 2n number of patterns or bits in this case to control the set and the reset line. So, that is actually a cumbersome process. Then I found out the real great design in VLSI testing, that is the scan chain, which solved most of the problems. So, what the person said that if you already have a shift register, if you already have a series of flip flops in the circuit, why not use them as scan registers, or why not use them as shift registers? So, he said that I will not use any extra shift registers to control the flip flops, rather I will use my circuit in 2 modes. In one mode is the normal mode, when the output of the next state function block will go to the flip flops, and another mode what I will do, I will connect all the flip flops in a shift register mode, and the output of the flip flops will be connected to scan in pin or to the output of the previous flip flops. Already we have seen the architecture how a scan register works, and this now in the test mode you can shift in values to the scan chain whatever you require to control the flip flops, and if there are n flip flops you require n patterns to control the flip flops. So, you do save in n number of patterns compared to a shift register approach, and also we have seen that you do not require any extra kind of shift register, so you do not require any extra flip flop to do this and register based testing. Only the extra requirement is the mask, which is also very simple because you do not require set preset arrangements in the flip flop. So, the set preset arrangement extra area you can incorporate in the adding a multiplexer. So, all the problems almost for sequential circuits were solved by the scan chain problem, scan chain design. The only issue that remained is that to set the flip flops you require n bits. If there are n flip flops in the circuit, you require n bits or n clock pulses to control them. So, only that part remains. All other things are solved using this scan register based design. So, today what we will see in details about the scan chain, how they are designed and how can you optimize on the number n. So, if there are n flip flops, you require n number of bits to control the flip flops. So, if we will see whether we can decrease that and many other things we will try to see about the scan chain today. So, first we will start with the example. So, you remember this was our old circuit we are considering every day. So, in our lecture, so there was a stack at 0 fault and there is 2 registers. If you recall, to test this stack at 0 fault, you require a 1 over here. So, D is propagated, you require a 0 over here. So, you require a 1 over here. So, you require a 1 over here, you require 1 over here. Similarly, you require a 1 over here and also you require a 1 over here. So, we know that this is one output of the flip flop and this is another output of the flip flop which has to be controlled by any means. So, you can we saw that by controlling it by set reset lines, and also saw by controlling it by a shift register where you have put 4 flip flops and so on. So, now we will see how it can be done by using the scan chain. So, the main idea is that this one is to be 1 and this one is to be 1 has to be done. So, already discussed what we will do in first step, we will make m equal to 1, that is this thing removes the next state function block from the circuit and fixes the connected in a scan chain. So, as already said that if you make m equal to 1, that is test mode equal to 1, if you do, then what happens, then this series of flip flops get decoupled from the circuit, that is the next state function block it gets decoupled from and it gets connected in a chain mode. Then in this case you require a 1 over here, a 1 over here. So, you require 1 and a clock pulse, then you require 1 and a clock pulse. So, 2 1 with 2 clock pulse width will get the flip flop set to 1. So, let us just look at the circuit architecture a bit in details. So, what happens? So, you make m equal to 1. So, this is the normal input from the NSF block. So, which is cut. You can see that the output is not there, it has been cut by the flip flop. Similarly, this was the output of the NSF block which is going to the flip flop number 2. So, that is also cut by this making m equal to 1. So, what happens? This scan in this external pin that get connected to the flip flop, output of this flip flops get connected to the input of the second flip flop and this final output is the scan output. So, now it becomes a shift register chain. So, you apply 1 1 at the rate of 2 clock pulses, then what you will have? You will have 1 here and 1 here. So, this actually sets your flip flop. So, you can understand that what we have achieved. So, in the previous, if you are using a scan register, shift register to do this. So, you require 1 0 and 1 0 because set equal to 1, reset equal to 0, then again set equal to 1, reset equal to 0. So, pattern of 1 0 1 0 needs to be shifted kind of a thing to make it, but in case of shift register only you require the pattern 1 1 to control the registers flip flop. So, the registers of the flip flop. So, if there are n flip flops, so you require only n patterns in case of scan register based testing and 2n in case of shift register based testing. So, not only this scan chain actually solve the problem of extra number of flip flops in this series what you call the register, but also it solve the problem of reduce the number of time required to move in the values to required to control the flip flop. So, in this case it is if the n flip flops maximum n patterns is required to be shifted. Now, what happens? So, now you get this one as 1, you get this one as 1, now it is done. Now, you have to apply a 1 and a 1 as we know to get the flip flop or the fault tested. So, now what you have to do? You have to make m equal to 0. So, already discussed that when m equal to 0, then the scan input or the scan chain gets decoupled from the circuit and the normal NSF block gets connected to the circuit. So, if this is done, then what happens? This is the normal operation of the circuit. So, what you will get? So, you are having a 1. So, I can apply 1 1 over here. So, you get a D over here, you get a 1 over here and then you get a 0 over here and you get the output and it is tested. So, this is there is only 2 patterns required to test the fault. So, we should not call it 2 patterns, we should call this is the final pattern which actually applied to the primary output to the tests and 2 bit shifts were required, 1 and a clock pulse, 1 and a clock pulse to do this kind of to set the flip flops. So, you require n, that is here n equal to 2 plus 1 number of patterns to test the fault. So, in case of shift register based testing it was 2n plus 1 and in case of, if you remember, in case of set reset line testing. So, in case of set reset line testing circuit, I mean test pattern, we required only 2 patterns. One pattern was directly required to set and reset these 2 flip flops and one pattern was this one to do the testing. But in that case the extra number of pins became so high that actually it killed us all. So, therefore, we had to go to the scan chain based business and everything was solved. So, I mean only disadvantage in this case we have found out is that we require 2 patterns, I mean n number of patterns to shift this flip flop. So, if there are 10,000 flip flops, say for example in your circuit, then the problem is that you have to have 10,000 clock pulses to set the flip flop first or reset the flip flop first, and then only you can apply the final pattern. So, that is the only problem that is remaining with this scan chain. All other problems have been solved because no extra area overhead for the shift register, and you can say that I have put some multiplexer. So, what is the consequence? Putting the multiplexer does not have any much consequence here, that you have to understand, because already told that when you are having the scan registers, you can see we do not have a set or a reset line is not there, these lines are not there. So, whatever area we save by putting this, so you can say that by eliminating the set and reset lines, now can be you can say that I have got this advantage by, I mean whatever I have saved by removing the set reset lines, that part of the circuit I can add for the multiplexer. So, there is, I mean we should not say that there is exactly same amount of circuit you are saving is used by the multiplexer, but what some area we have saved because of not using the set reset lines, and we can do it in this way. So, this way you can understand this is a basically you can say in a broadly quote unquote saying, not in a very absolute terms you should think, but you can think of in this way. So, now we are trying to solve the main problem that remains is n number of patterns to set it. Okay. So, now let us see another advantage, that actually now to solve this problem we will get another byproduct, we sometimes say this another byproduct we will get as we will see here. So, we will get another advantage of using this scan chain as we will see. So, one advantage will be this n will be reduced, and secondly we will see that we are getting another advantage. So, slowly we will come out. So, what happened if we saw that if you are using the scan chain till now whatever we discussed, so you are using the shift registers mode, you reset mode. So, what we have to do, first step was remove flip flops, that was the first step, and second de-algo. So, you remove all the flip flops from the circuit and we perform a de-algorithm. So, they are the two basic steps, remove the flip flops and remove all the flops and do a de-algorithm. So, whole circuit you have to apply a de-algorithm, but now we will see that by using scan chains you need not to do de-algorithm on the whole circuit, you can only take a partial circuit and do this. So, let us say this is a new circuit, we have added this part of the circuit to illustrate the concept. So, let us take a stuck at 0 fault over here. Now, if I say that I want to use the standard which we were discussing, so what you will do? You will remove this flip flop, you will connect them here, you will remove the flip flop, connect it here, you will remove the flip flop, connect it here, and do an ATPG on the whole circuit. But, so it takes some time and complexity. But now, we will see that if you want to do this, another advantage which we will see that in case of scan chain, you did not consider the whole circuit for the ATPG. So, what we will see? First, you have to find out entire circuit you require, eliminate the ATPG on circuit. So, new advantage will eliminate the ATPG from the whole circuit as well as this n factor will also come down. So, we have to find out what? We have to consider the input of the nearest flip flop from the fault size as an output line and perform ATPG on the sub circuit lying in the cone of influence of the nearest fault. So, what we have to do basically? We have to find out a flip flop actually which is nearest to this fault site. So, if in this case you can think that, so this is my, you can think my nearest flip flop input, okay, because this is quite far, this output is quite far, and this input, the input of this flip flop input does not come under the influence of this fault site. So, you can think that this is the nearest input of the flip flop which is nearest from the fault site. So, just consider the nearest input and then make a cone of influence, then you have to find a cone of influence. So, what do you mean by cone of influence? Cone of influence is nothing but, say for example, So, what do you mean by cone of influence? So, cone of influence of this gate, say of this gate output is actually input A and B. So, that means this output is dependent on only on these two inputs, okay, and not on any other. So, a cone of influence of any point in a circuit is all the inputs and the gates which influence. It is a very simple definition. Okay, so, in this case you see this is the point. So, which gates are involved in this one? So, this gate is involved in this D and E are involved and this flip flop is involved. So, only this sub circuit is involved in this point. So, the cone of influence is only about this very small circuit part of. So, if I make a cone of influence at this point, so I will have only this part of this circuit. So, what you have to consider? You have to consider only this much small circuit for this ATPG, because you have to first find out the nearest flip flop and you have to do that. So, we will just see what we have done. So, just remove the flip flop, all the flip flops have been removed. Now, you do not consider anything else. Okay. So, we will show you the advantage in steps. Okay, so just we will see the, I mean that this is what is the advantage we are going to get, that what we will do, we will just consider the small circuit, only small part of the circuit over here and do ATPG and solve the problem. Okay, but if you are taking the normal approach, that is removing all the flip flops, doing ATPG and all those things, so it will take a roundabout approach. So we will compare both the approach and show that what is the another advantage. Okay, so now let us see that this is the whole circuit after all the flip flops have been removed. Now let us consider the path. This one is the path. So we are taking the traditional approach now. Another advantage will, because we show the real advantage of the scan chain business, then you have to compare both the approaches, that is traditional approach and the scan chain approach within the traditional scheme. Okay, that is consider the whole circuit and do that, so that you can see exactly what is the advantage, then it will come out. But if I just show you one approach, then that is the newer approach, then that will not give you that much high feeling. Right. So let us say the path. So what is the path? So let us say the path is D, this is the path, then you say that I, so this is the fault path, we are taking this is the I, then we are saying O, okay, correct, then it is P, this P and then M and D. So this is the path the person has selected for fault propagation, because there can be any another path also. If you can see that there can be, there is another X path, this path also you could have taken, this is another path, like from this there was another path that could have been taken for the fault propagation, but this has not been selected because from here there are two D frontiers, from this gate there are two D frontiers, one is this, from this gate is one D frontier over here, another D frontier with the down line. So any one could have been taken, but the person has selected this one, so let us go about it. So this target 0 fault, so you put a 1, so you get a D prime over here. Now you get a D prime over here, you require a 1 over here. So to require a 1 over here means there is a flip flop over here. So somehow you have to make it 1. So that you can easily do by scan chain by setting it to be 1, correct. Then you take D over here and then you get a prime, the inverter, so you get D over here, right. This is the OR gate. So to get a D over here, you require a 0 over here. So to require a 0 over here, we require a 0 over here, and then finally we get the D at the output. So for that you require a 1 over here. Okay. So to get a 1 over here, you require a 1 over here. So there was a flip flop over here, so there you have to again get a 1 over here. So that is actually another flip flop. So by scan chain you have to control this flip flop output to be 1 and this flip flop output to be 1. The second flip flop output now is X, you do not care. So this is about the traditional ATPG or sequential circuit using scan chain. So this is what we have got. So you require 1 1 0 1. X, do not care, this flip flop has to be set to 1, the final flip flop has to be set to 1, that is the F3 flip flop has to be set to 1, the middle flip flop need not be care, do not care, it is an X over here. Then you can test this stuck at fault. Okay, now let us see what happens. So first we know that you have to set these flip flops. So now set the flip flops means you have to put this, you make M equal to 1, so you can see that this scan chain is connected, this part and this part of the circuit is totally decoupled. So what you have to apply? You require 1 x1 and 3 clock pulses, because the middle one you do not bother, this has to be 1 and this has to be a 1. So you require 3 clock pulses. So as already discussed in the traditional scan chain based testing, so if there are n flip flops, so you require n bits to be transferred. Okay. So now if you just do that, so whatever the flip flop requirement, like this has to be a 1 and this has to be 1, you can easily obtain. Okay. Now what you do, so that is has been said, would apply the pattern to sensitize this fault. So here actually you have to apply a 1, that is that we can know that, but 1 and a 1 has been done. So this is what the flip flop has been taken care of in the scan chain. Next what you do? Next you make M equal to 0, that is our traditional approach and the standard approach of flip flop, scan based flip flop. So once this is done, so this scan part is decoupled from the circuit, so this part is decoupled from the circuit. Now what happens? Normal NSA block output is connected, so you can see that this is 1, so you are getting a 1 over here, so you are also, this is not required anymore. So now what we do, you make apply D equal to 1. So if you apply D equal to 1, then what we get is this case, so stuck at 0, so it is D prime over here, and then you get a D prime over here. I put a 1 over here by scan chain, I have controlled the flip flop, so you get a D over here, sorry, you get a this is D prime, sorry, it's a D prime over here, and then D prime is over here, then this is an inverter, so it will be D over here, because now we get a 0 over here by applying C equal to 0, and then it has come out because this gate is this flip flop is controlled by a scan chain, and you get the advantage and your flip circuit is tested. So in this case we required 2 patterns, we required 3 patterns. What is 1 x 1? So this one applied at 3 clock pulses, and finally we applied the pattern C equal to D 0 and D equal to 1. So this is the pattern we apply, others are excess, then we get the circuit to be tested. So 1, 2, 3, and this is the 4th pattern. So in 4th pattern we have done the testing using a scan chain. Now, the another advantage which we are going to see, that one we are going to now discuss. So, in this case what we have seen, so we have considered the whole circuit for the ATPG, that is one problem. If it is a big circuit, so combination, even if it is a combinational ATPG by D algorithm, it takes some time, because there, in this case there was no backtracks, but there could have been backtracks and all the problems. So, we have considered the whole circuit, and secondly n number of test patterns are required to set the flip flops, because in this case there are 3 flip flops, so we require 3 patterns to do that. Now, again what we are saying that now we will take the new approach, in which case we saw that this flip flop was here and this Tuckett fault was here. So, this was the, this is another flip flop was here. So, this is the nearest input to the flip flop, that is what is the question. So, that is, this is the nearest from the fault side, this is the nearest flip flop where we could have reached from the fault side. So, just we will forget about the whole circuit, this whole circuit you can think, this whole circuit you can eliminate, this circuit also you can eliminate, only we will consider the circuit from this point, that is the input, this point, the cone of influence. So, only this sub circuit we are going to consider. We are going to consider this flip flop from this flip flop, and all the circuit only influencing by the cone of influence from the flip flop. So, only the small sub circuit will come into picture, this gate will come into picture, these 2 flip flops will come into picture, and these 2 inputs will come into picture, nothing else. So, only we will do ATPG on this, and we will forget about the whole circuit. Okay. So, that is the big advantage we are going to see over this. Now, what we are going to do? So, we are applying, this is the stuck at 0. So, you have to apply a 1. So, you get D prime over here. Now, you require a 1 over here, correct, because you have to fault effect has to be propagated. So, you get a D prime over here, correct, and for that you require E equal to 1. E equal to 1 means these are flip flops. So, this by way is scan chain. So, we can set it, and this is the case, and so the fault effect is here, which is at the input of the nearest flip flop from the fault side. Your job is done. We do not require any other part of the circuit, and you see your ATPG even by D algorithm is very simple over here. So, you just consider this small sub circuit and you have done your job and you are done. So, what is this? The fault effect needs to be propagated to net J only, which is the input of flip flop 2. ATPG is performed with sub circuit which lies in the cone of influence of this one, which is only the small part. Okay, and pattern D equal to 1 will do your testing. So, your job is done. So, obviously, this is a very simple approach, and you have what you have, I can say that your combinational circuit ATPG complexity has been reduced greatly. So, that is the thing. Now, what we do? So, now that is what is done. So, you only know that this is equal to 1 and this equal to 1 will do the testing for you. So, for that only one requirement was that, so this flip flop will have to be set it to 1 by this scan chain. Okay. So, what you can see that we are again saving greatly, because we did not control these 2 flip flops. That is another important advantage you have to remember, that we are not requiring to save these 2 flip flops. In the previous case we required 3 pulses to set these flip flops, but now we do not require to do all this, because we are only considering a small portion of the circuit to do our job. So, only 1 clock pulse and 1 flip flop scan in is there. So, scan chain is there, but we do not bother much. So, we just give m equal to 1 and we set the flip flop. So, you can also think that if there is a fault here, okay, that you can say. So, in this case this will be the nearest place. So, in this case to test this what you call, to set this flip flop for some reason or the other, then you have to apply 3 what you can call 3 clock pulses to set the flip flop. It is far away from the scanning input. For in that case you have to go to the worst case, where if there are n flip flops, then you require n patterns to set or reset the flip flops by scan chain. But all the flip flops will not be farthest from the fault side. About you can, if you go for an average, so half of the flip flops will be near, very much nearer to the fault side, and half of them will be farther, because every time we are going to, in an average case, we are always going to find out the fault which is nearest to the flip flop. So, there will be a great deal of saving if you look at the average case. So, in this case, say for example, the first flip flop has to be considered, so only 1 clock pulse will set the flip flop as required. But if it is the farthest, you require 3. So, if it would have been somehow the second one had to be set, so you can set it in 2. So, sometimes in average cases there will be lot of saving in the number of patterns required to set or reset the flip flop. So, in this case it is 1, so you have saved 2 patterns. Now, what you do? So, now this is done. So, you do this. Next, what you do? You make m equal to 0. So, obviously, the circuit starts operating in the normal way. So, now what you do? So, you know that you apply a D equal to 1 over here. So, if you apply a D equal to 1 over here, so it is D prime. So, D prime is there, and this is 1. So, you get a D prime over here. So, you have propagated the fault value to the input of another flip flop. Now, we have to again use another mode, which was not required in case of this scan chain based testing we discussed earlier. So, in the previous stage, what we do? We set and reset the flip flops, you give the primary outputs that sensitize, propagate and justify the fault to some primary output, and your job is done. But here, the next step for this advantage to get, where you are considering a sub part of the circuit, doing ATPG on that and propagating the fault effect to the nearest flip flop. So, again there is third step involved. In this third step, what we do? We again, okay, so this is actually what I said. Okay, so this is this was the case. So, this I got the fault value I have got over here. So, this is the pattern I have applied. Now, what you do? So, there is one more step you have to take into picture, that is very important. So, initially if you remember in the last case there were two steps, set and reset the flip flops using scan chain, then get the fault value, propagate the primary output. But here there is another step involved. So, in this case again you have to make m equal to 0, okay, and apply a clock pulse. So, if you apply the clock pulse, what will happen? This D prime, the fault effect which was at this input, get loaded to the nearest flip flop output to be selected. That is one important thing you have to do. So, the what is the added step you have done here? The added step is that you have to again go for m equal to 0 and give a clock pulse. So, that is D prime, the fault effect get recorded in one of the flip flops selected. Now, again there is a fourth step. So, two more steps we have added. In the fourth step, what you have to do? You have to put some x in this, in the scan in, do not bother, and keep some clock pulses. So, this fault effect gets out through your scan output. So, two more, see what I have done. So, in the first case, previous approach, so you give us take a scan chain, set the scan chain, apply the pattern and get the fault effect to the primary output. Your job is done. But here you have to consider all the flops, set the fault, for all the faults to end patterns and all this business were there, as well as you have to do ATPG on the whole circuit. That was a big problem. So, now how I have solved it? So, in this second approach we have considered only a partial circuit which falls under the cone of influence of what? Which falls under influence of the nearest flip flop to the fault side. So, once that is done, so what you do? You do ATPG on the small part of the circuit, so there is very less chances of collision and all. So, your job is done. So, that saves a lot of your time and computation efforts for the combinational ATPG. Now, what you do? Next, you so this is done. So, you set next you set the flip flops, whatever is required. Now, all the flip flops will not required to be set, only whatever are required you set them using your what you call your scan registers. Once that is done, so your fault effect will be propagated to the output of the flip flop selected, nearest flip flop selected. Then there are two more steps to be done. Now, you go to the M0, that is the normal mode, and you apply a clock pulse. So, your fault effect will be recorded at the output of the flip flop which was being the nearest flip flop selected. Now, so that was done. So, your flip flop value it was selected over here. Now, what you have to do? Now, we have not considered to propagate the flip flop this fault effect to the output of the primary output. So, what you will do? You will use the scan registers or the scan output to propagate this value. So, you have to again apply the output through the scan chain, okay, whatever was the nearest. I mean there is one more flip flop which has to be passed to get the output to the scan register. So, you just apply 1 x, you don't, because you don't need to set or reset any flip flop, you just need to bring out the value. So, here you give one clock pulse and your value will be passed out to the flip flop. So, here you have to understand that we have not much saved about the clock pulses, because one pulse was required to set this flip flop, one pulse was there to record the value, and one pulse was there to take out the value. So, in the previous case we required 3 clock pulses to set the flip flop, here 3 pulses are required to set the flip flop, record the value and bring it to the output. So, there was not much saving in that, but what we save greatly is that we have to perform ATPG on a very small part of the circuit, and if you do that there will be very less chances of collision and you will be always getting successful results. So, this is another very big advantage of combinational sequential circuits, D algorithm, advantage of scan chain based testing, that you can perform ATPG on very small parts of the circuit, and that will greatly reduce your chances of collision, and almost all the faults you can test very easily in one go. You can go for the ATPG. So, that is what we are seeing. So, that is what we are going to, that is what is another advantage. So, in case of ATPG using a scan chain, that is you have to do ATPG on a very small part of the circuit. And secondly, like sometimes you may be saving in the number of clock pulses to set the flip flops. Okay. So, that is the two advantages of using the scan chain. So, what people do? People generally do not go for full circuit ATPG. In case of what you call scan chain based testing, they do the cone of influence and do it for the partial circuit, and then they bring out the fault effect to the scan chain rather than bringing out by what you call the primary inputs. Okay. So, now that, so we have what we have seen. So, we have solved the problem. We have got one advantage, that ATPG has to be done on a smaller part of the circuit, but one disadvantage still lies that n factor, that if there are n flip flops in the circuit, you require n patterns either to control the flip flop to bring out the value is not yet solved in that way. So, we will try to solve it in a different way, which is actually called the partial scan chain. Okay, so, we will see what do you mean by a partial scan chain. So, if you just recall what we have discussed in the previous last lecture in sequential circuit testing using what you call this sequential circuit using time frame expansion method. So, what we said that to set a circuit, all the flip flops, if you do not consider scan chain, to set all the flip flops or reset all the flip flops in the circuit using time frame expansion method, we require at most sequential number of clock pulses, because if you assume that all the flip flops are connected in this fashion in your circuit, then maybe sequential, that is the last flip flop is dependent on the previous flip flop, then it is dependent on the previous flip flop, then dependent on the previous flip flop and so forth. So, the sequential depth is maximum in this case. So, you require n, if there are n number of flip flops, so sequential depth max can be n, and what is the number of clock pulses required to do the testing or set or reset in case of pure what you call this time frame expansion method will be D sequence, that is equal to n, but that will be the worst case when all your flip flops are connected in a chained fashion. But generally if there are n flip flops in the circuit, then D sequence will not be, it can be the max and the worst case equal to D sequence. NFF, the number of flip flops will be equal to D sequence in the worst case when everything is connected in a chain. But there can also be the cases when, or in the general case, the number of flip flops will be much larger than D sequence. So, if you are considering what I say, if you are using a time frame expansion method, then you require D sequence number of bits to set or reset the flip flops, or D sequence number of patterns to set or reset the flip flops. But in case of scan chain, you always require n. Now, if the NFF is the number of flip flops, you always require around NFF number of patterns to set or reset the flips or to bring out the values. So, one advantage at least we could see from the what you call the previous approach of time frame expansion method, that number of patterns to set or reset the flip flops is D sequence. It is not, in the worst case it can be as high as NFF, but always it will not be the case, always it may be less than equal to the number of flip flops. So, partial scan chain will take the advantage of your scan chain based approach, and your time frame expansion method advantage also it will take, because if the this D sequence number is less than the number of flip flops, then you can use less number of less number of patterns to set or to the reset the flip flop. But actually, if you remember, in case of scan chain as we are discussing, you require just single bits to set or reset the flip flop. But in case of your what you call this time frame expansion method, it is not bits, it is patterns which require to set or reset the flip flops, which are computationally very expensive. So, we will take advantages of both of them and we will see what we can do. Okay. So, we will again illustrate by examples. So, partial scan takes idea from both of these methods. This basic idea is to scheme to make only scan enable in those flip flops which are cyclic and remember as normal. So, what is the idea? The idea is that we have already seen in one example of the XOR gate. So, XOR gate what we have seen? So, if you XOR gate, if the cyclic XOR gate, so the XOR gate cannot be controlled and fault cannot be tested. So, for that case it is mandatory that it should be having a scan to directly set or reset the flip flop. But for other cases you may not have a scan chain. It can, because it can be controlled through partial which can be controlled through time frame expansion method, because in time frame expansion method the offline complexity is high, there can be clashes and all those things are there, because if you remember that when you are computing what patterns are required to control these flip flops in the time frame expansion method, the offline computation approach. But we said the computation is very high. Why it is very high? Because there may be clashes and all these things and you have to reiterate. But once if you have somehow found out the pattern, then the number of patterns required to control the flip flops will be much less than n. It will be equal to D sequence, which is much less than n in most of the cases. But in case of flip flops, you do not require patterns to control the flip flops. What do you require? You require bits. So, your getting of clashes and all is almost 0. But if there are n flip flops, you have to apply n patterns to do this control. And so, in the real time testing, when your chips are there, so you require n number of bit patterns to set it. But in case of partial scan or time frame expansion method, you require only D sequence number of patterns to do this. So, in time frame expansion method, you do lot of time in the offline, but when you are going for online testing, that is only when a chip is placed and you do in situ testing, so you do save in test time, which is more important if you remember our introduction class. So, we have to go, so people decided that we will take advantage of both. So, we will give scan chain to only those flip flops where it is very difficult to, if there is cyclic business, the flip flop is not controlled, then you cannot test your circuit, all those impossible stuff are there, then you will have to mandatory to put this scan chain. So, because you require directly to control this flip flop. But for other cases, if you remember, where you can do control by the time frame expansion method, you better use that, because your offline complexity is high, because you cannot control the flip flops using bits, you have to do by patterns in case of your time frame expansion method, but still the number of these patterns are less compared to n, which is D sequence, which is much less than that. So, that is the basic idea. So, we will illustrate by example. So, let us look at this circuit where there are two flip flops over here. So, this somehow they have been removed and ATPG has been done. So, now you can say that, say to test this stack at 0 fault over here. So, what we require? So, we require a 1 over here. So, the value of will be D over here, it will be a 0 over here. So, you require a 1 over here, that is a well known fact. So, this 1 will be required over here. To get a 1 over here, it is obviously you require a 1 over here, okay, and to get a 1 over here, you require 1 over here, we get a 1 over here. So, this is 1, but a big problem here occurs that to get a 1 at the output of this AND gate, you require M also to be 1. Okay, now this is a cyclic business. Why? Because you see, to get a M equal to 1, okay, you have to make J equal to 1, that is very important. If J is 1, then only M equal to 1, and to get J equal to 1, you have to get M equal to 1. So, this is lying in a cycle. To get M equal to 1, you have to get J equal to 1, and to get J equal to 1, you have to make M equal to 1. So, this is a cycle, and this fault cannot be tested. So, what you have to do is that you have to apply a partial scan chain. Okay, what is the partial scan chain? That is, you have to somehow get this value to be equal to 1. So, if that is done, then this you can use a time frame expansion method, because here you require a 1, but you do not require a flip flop over there. You can go for a time frame expansion method, and you can use this C1 and in this 4 to get this one. Okay. But this one controlling to be M is a very difficult problem, because it is a cyclic pattern. So, for this you have to require a scan chain, otherwise this is not done, because what you can do is to get a 1 over here. So, what we can do is that you have to somehow make this as 1 by using a scan chain, and this input is directly controlled to be 1. Then if you apply this, then only M can be directly 1. So, using this flip flop only scan, you can get M equal to 1, but for this flip flop you do not require a scan chain, you can directly use time frame expansion method and your job is done. Okay, so, let us see in stepwise how can do that. So, by time frame expansion method, you just you make J equal to 1, we get J equal to 1, all this thing has been explained. So, let us see what we do. So, first what we do, we make a scan chain. Okay, so, this is your scan frame and this is your non-scan flip flop, that is why we call it as a partial scan chain. So, this is your partial scan. So, in this case what you do, you first make M equal to 1, you can do, then you apply you apply a 1 and a clock pulse. So, once you do, you get a I equal to 1, definitely will get. Okay, next what you do, that is what has been done, you make M equal to 1, apply a clock pulse, you get a 1 over here, that is what is being done over this case, correct. This is what I was saying, that this we control by time frame and this you control by scan. Okay. So, now this is the first step. So, you just M equal to 1 you get over here. Now, what you do? Now, you make M equal to 0, so that your circuit comes to a normal fashion. Now, what you do? Now, this what also you require a 1 over here. So, for that there is no scan chain, you will not use a scan chain, as already said, we will be using time frame expansion method. So, in this case you make C equal to 1 and apply the clock pulse. Okay. So, if you apply the clock pulse, what is going to happen? You are going to get a 1 over here. So, that is very obvious. Okay, now you get a 1 over here, you get a 1 over here, and then you apply a 1 over here and a 1 over here. So, if you apply a 1 over, you get a 1 over here, and then you get a 1 over here, you apply this, so you get a 1 over here. So, this is a 1. So, finally, this will also be a 1, this will be a 0, and your circuit is going to be tested. So, essentially what we have done, so in this case you do not see much advantage of your this is the direct primary input flip flop. So, you do not directly get the advantage of what you can see, what I was trying to highlight, but what is the basic concept which I was going to discuss on the partial scan chain, you have to see it a bit more careful way. So, what is the idea we have seen? That if there are, so say if we have used a direct scan chain based approach, so what would have been there? Say there would have been 10 flip flops over here, something like this. So, all are being connected, say there are 10,000 flip flops in a chain. So, what you have to do? So, you require 10,000 clock pulses to set or reset them as required, correct? But let us assume that the sequential depth, that is DFF, the sequential depth, okay, is say for these flip flops are say 500. So, or say 500. So, what do you mean by that? That means all the flip flops are not actually by combinational circuit, this is a scan. So, whenever you are doing it by a scan chain, then what you have to do? You have to connect all the flip flops, as if you remember, all the flip flops has to be connected in a chain. So, if there are n flip flops, you require n patterns to set it. So, if there was only one flip flop here, so you have to take one pattern. So, if there are another 10,000 in this scan chain, you require 10,001 clock pulses to do that. But the sequential depth of this circuit is much less than that, because in the normal circuit topology, if you consider, all these flip flops will not be dependent on other. Like the 10,000 flip flop will not be dependent on the 9999th flip flop. Similarly, the 9998 flip flop will not be dependent on this, that is not, it will not be the case. So, what can happen is that some of the flip flops will be dependent on the others and so forth. So, in the average case, you may have 10,000 or 1,000 or 800 or something which is less than sequential depth. That means, there are some around say some 500 flip flops, there are combinational circuits in between. So, these 500 flip flops are dependent, last flip flop is dependent on the previous one and so forth. There can be another separate symbol chaining like this. So, your sequential depth will be different or your maximum sequential depth will be much less than 10,000. So, what you can do is that all those flip flops which did not be directly controlled because of this cyclic business, we keep them in the time frame expansion method. So, in this case if you consider this is the only flip, this is the dangerous flip flop, its sequential depth is 2. Because this flip flop output is dependent on this one. Here the sequential depth is 1. So, the overall sequential depth of the circuit is only 1. So, what you have to do? You require one pattern to test this circuit. So, had there been, for example, just let us extrapolate the example. So, I have just considered that this is a OR gate with several other say tens of other flip flops. So, other 10 flip flops are there, just consider this. Okay, so, other 10 flip flops are there, say 100, say 10 flip flops others are connected to this one. So, there are all other flip flops are there. So, another 10 flip flops are there kind of dot. Okay, and they are all connected to the primary input. So, what is the sequential depth? The sequential depth of the circuit is 2 for this one, because again this is a dangerous flip flop kind of a thing, because dangerous part of the circuit for testing because the feedback. So, this you have to control by scan, no option about it. So, done. Now, considering this and all these 10 flip flops, what is the sequential depth? The sequential depth is again 1, because this flip flop is dependent on primary input, this is primary input dependent and so forth. So, if you require a scan chain to set all these, because it is a OR gate to propagate the value of D over here. So, all these outputs should be a 0. So, if you use a scan chain, then what I have to do? You have to make a scan chain from all these flip flops of this one. So, there will be 11 flip flops in series. So, you require 11 clock pulses to control this one. But the sequential depth is not 10 or 11 in this case. The sequential depth is 1, because all the flip flops here are dependent on the primary inputs. So, what you have to do? You have to apply. So, in this case a 1 is required. So, you apply a 1 over here and all zeros you apply, and you apply a single clock pulse. So, this is my time frame expansion method. The pattern is 1 0 0 0 0 10 zeros. So, once you do that, you will get the output all 0 over here and a 1 over here, and your testing is done. So, had it been using a scan chain, so you have to control in this way. But if you are directly using a what you call this time frame expansion method, then only one, if the sequential depth in this case is 1, so you require one pattern to do that. But here the assumption was be simplistic, that all the outputs or inputs of the flip flop are the primary input, so the controllability was easy. But even you can have a combinatorial circuit, then you have to do some more computation to do it. So what is the advantage of the partial scan we have got? The partial scan chain advantage which we got is that you may not require n number of patterns to control the flip flop. So, that point is also solved. So, what we are doing, but again it is not, you are not being able to solve all the problems. So, what has been the ideal situation? The ideal situation what has been that we could have totally thrown over the time frame expansion method, we could have already taken the scan chain based approach, and then we could have solved that you do not require n number of patterns to set the flip flops. But that we could not do, because if you want to use a scan chain, totally a scan chain approach, then the advantage, one of the greatest advantage is that you do not require to do ATPG on the entire circuit. You can take, what you can do, you can take ATPG for the nearest flip flop, and then you can apply your test pattern, and you can do your ATPG for the small circuit and take out the value through the scan flip flops, and then it is done. But again for driving, for setting the flip flop, recording the value at the output of some flip flop, and again bringing out through the scan chain will require n number of clock pulses. So, that could not be solved directly using a scan chain. So, indirectly what people have taken, for that is the best solution, that partially you take flip flops for scannable and partially you take them for what you called this time frame expansion method, because time frame expansion method can be solved, it requires less number of patterns to do that, only the offline complexity may be high to set the flip flop. That is only the sequential depth, that much is required. So, you do that, and then if there is some cyclic points in your circuit, for that you require a scan chain to solve the problem. So, this is somewhat we have gone for a trade off, and this is where our combinational circuits are tested, that you go for the sequential approach, put partial scan for the flip flops which are not directly controllable because of cycling problem, and for other you use the time frame expansion method and you do that. So, this is one of these, now there can be lot of trade offs. So, you can think that I will keep only few parts, some, because if one scan chain becomes very long, then you can have some problems. So, you can think of again going for another hybrid business, that some of the circuits, some of the flip flops, even if they are they are non-cyclic, I can go for a scan business, because time frame expansion method may be too high in complexity. But so we'll just see in the question and answer session. So, we will come to the question and answer and ask these questions. So, two approach, one approach is full scan based technique, and the second approach was partial scan and partial sequential problem. So, can there be any third hybrid approach for this one? So, we will see. So, how can test time be reduced for this for the circuit shown below? So, this is another circuit below. So, everything is scan based. So, now how can you reduce the test time? So, if there are T flip flops, so you require 3 clock pulses to set the flip flop, because the scan chain will require 3 clock pulses. How can you reduce it? So, you can say that there is no cyclicity in this business, and so what we can do, we can go for a what you can call this time frame expansion method. So, time frame expansion method, what is the sequential depth of the circuit? For this is 2, because this is dependent on this flip flop. Here the sequential depth is 1, and for this circuit the sequential depth is also 1, because it is directly controlled by this one. So, you require 2 patterns to set or reset the flip flops. Okay, but in case of this for time frame expansion method, but if you are using a full scan chain, then you are required 3 patterns to do this. So, you can say that I can do that, but for that you can tell that, because there is some, because that in that case if you go for time frame expansion method, then your controllability will not be just by zeros and ones, it will be patterns required to control. So, there will be offline complexity, but still you require only 2 patterns to set or reset the flip flops. But people have then gone for another third approach, in which they call that multiple scan chain. In what case is multiple scan chain? They say that don't make a very long scan chain. Why we require 3 pulses to control it? We require 3 pulses to control these flip flops, because they are 3 in chain. So, he said that why are you making such long scan chains? Because people directly want to avoid this time frame expansion method because of these mathematical complexities. So, what they say that make multiple scan chains. So, what this guy has done? So, he has made one scan chain over here and the scan chain over here. So, in this case if you do, then there are 2 scan chains. So, you can parallelly load them and shift the data. So, in this case there are 2 patterns. So, you can load one here, and 1 clock pulse will load here, second pulse will load this, and parallelly with this you can load this. So, if there is another flip flop over here, so these 2 can be loaded together. So, if you have say 10,000 flip flops, say, so if you make say 10 scan chains, so you will have 1000 flip flops in one go. So, now you do not require 10,000 patterns to set or reset the flip flops, only we require 1000 to do that, because you are loading in parallel. So, that is one thing, that is one greatest advantage. The third approach, which is now widely accepted, people generally do not go for what you called this time frame expansion method and partial scan. What people rather do is that they go for multiple scan chains, because I mean time frame expansion method is very difficult to do offline, and sometimes there will be clashes, and you do not require patterns, you do not require bits, you require patterns to control them and so forth. So, what people do is that they go for multiple scan chains. So, they break up the long chains into partial chains and you load them. But there is a problem. So, if I say that, so if you make 10 chains, then you require 1000 patterns to bits to control that. So, let us say that I make 1000 such chains. So, this 10,000 I make 10,000 flops were there. So, I bring 1000 chains. So, you require 10 flip flops per chain. So, you are very happy. So, you require only, so there are each of these chains have 10,000 flops. Sorry, you make 1000 chains. So, okay, if you make 1000 chains, then what is going to happen? If you make 1000 chains, then if you make 1000 chains like this, say chain 1, 2, dot dot dot. So, 1000 chains you make. So, each one will have only 10 flip flops. So, only 10 patterns are required, or 10 clock pulses are required to set it. So, your job is done. But here again there is a big problem, that is pin out problem is coming. For each scan chain you have one scan in pin and you have one scan out pin, and you can assume that the clocks are same. But for each scan chain you require 2 pin outs extra. So, if you have 1000 scan chains, so you require 2000 extra pin out, which is again very difficult. So, always there is a trade off. So, you can think that I will make say around 50 scan chains. So, there will be 100 pins. So, in a very complex chip, you can say that 100 pins for testability may be okay, but it is towards the higher range. So, it will be 10,000 by 50 if you go. So, you get it around 200 clock pulses to do that. So, again always there is a question of trade off, that what you will do, what you will achieve. So, testing is or VLSI design or testing is always about what you gain and what you achieve. So, either if you go for totally time frame expansion method, then if there is no cyclic business in the flip flop, then you are at the best, though no extra circuit, very less number of test patterns to go about testing, but again the offline complexity is very high and you require patterns to do this. Then if you go for full scan chain based approach, then you require a single scan chain based, then you require n number of patterns to set the flip flop. So, more test time is there, but here the chances of collision etc. is almost 0, because you will take small sub circuit of the circuit, part of the circuit to do the scan chains, when testability ATPG or very small sub circuits, and then but you require n number of patterns to do that. Then you can go for this partial scan, what you can call partial scan chain. So, here again there is a mix of scan chain and what you call time frame expansion method. So, complexity is there, but there again you can go for another simple approach. You can go for break up the long scan chain into partial small scan chain. It's a very good approach, but again if you are making too small size of the scan chains and more number of scan chains you are bringing out by breaking the larger one into very small number of very small size large number of scan chains, then pinouts will be higher. So you have to select the best and the worst out of it which you feel as the best for your design. This is how it goes. So again next question we see how can the flip flop themselves be tested in a scan chain based testing. So if you remember we said that the our fault model for sequential circuit we did not consider faults inside the flip flops, because we said that if it is there then your combinational circuit sequential circuit may be converted to virtual what you called sequential circuit can be converted to virtual virtual combinational circuits, because the flip flop may not change state, it may become static and lot of other complex issues will be there making ATPG very complex. So we assume that there is no faults in the flip flop, but still you have to test the flip flop. So how can you do that? Scan chain can easily do that. So in scan chain based testing, if you want to test the flip flops only, then you just go for the scan mode, make m equal to 1. Do not think about making m equal to 0, don't do that, make it only a scan chain and then pass this kind of sequence 0 0 1 1 0 0 1 is alternating sequence. So there is 2 zeros, then 2 ones, then 1 0 0 1. So this type of sequence you give, so you can get this type of transitions and the output of the flip flop from 0 to 0, from 0 to 1, from 1 to 0 and from 1 to 1. So this type of transitions you get at the output of all the flip flops. So if you get them correct, you know that your flip flops are fine, the flip flop is toggling fine, and so your flip flops can be easily testable. So scan chain in the end, another greatest advantage of the scan chain is that you can also test the flip flops. So again in the end if I emphasize that if there is one very good design or one of the best designs for testing which has been ever developed, so I will say that it is the scan chain, because it solved most of the problems that is related to your sequential circuit testing was solved by this scan chain. So with this we come to the end of this module and this lecture. In the next module, and the next two modules are remaining in testing, what we will see there? So next we have seen that this is your offline testing. So in scan chain based testing or whatever we have discussed till now, so patterns are generated and once your circuit has been designed, so it has been fabricated, it is placed on the tester, your tester will apply those patterns which you have determined throughout the lectures we have discussed. So some patterns are decided, so those patterns are applied by the automatic test equipment, you get the response and you say whether the circuit is normal or faulty. If it is normal, it is shipped to the customer, otherwise it is thrown out. But now say for example you have sent your chips, now it is put in my laptop or put in the video camera or put in the PC you are using, again it may go bad, because nowadays chips are very sophisticated, so it may happen that even during operation it may have some failures. Now how to test them? There is something called built-in self-test. So whenever your circuit starts its operation, so it will be testing itself, right. So that is one very important paradigm of testing. So that is one part which we are going to see, and also there is one thing which I have not considered, that is the memory. We have considered sequential circuit, we have considered combinational circuits, but we have not considered the third very important arena of circuits, which is the memory. So in the next few lectures we will be looking at built-in self-test and memory testing, which will complete our course on this thing. Okay, so thank you with this.